Hello, we are the Missouri S&T 2019 Drillbotics Design Team. The overall rig design is about the same as last year with a few major changes. Again, the vertical motion will solely be controlled by linear actuators. Due to misalignment issues seen last year, they have each been upgraded to actuators that provide position feedback so they may be precisely individually controlled. A challenge seen last year was our measurement of weight on bit with strain gauges attached to the drill pipe. This year we have eliminated them from our design entirely and opted for a through-hole load cell design. This will be mounted to the travel block and measure compression seen from the drill pipe when it contacts the rock. The load cell assembly consists of the sensor, thrust bearing, and shaft collar, all contained inside a machine casing. The shaft collar will be fixed to the drill pipe, and when the bit makes contact with the rock, the collar will apply a compressional force through the bearing to the sensor to obtain an accurate weight on bit measurement. As for the torque, it will now be calculated from the motor's efficiency, current, and voltage. To make a temporary space for electrical components while drilling, a foldable electronics table was also designed out of the same T-slotted material and a pegboard surface for easy anchoring. The legs are made of square steel that will allow it to easily collapse and be folded. On a safety note, we will now have plexiglass shielding framed inside of the T-slotted aluminum around the entire lower half of the drill as well as the traveling block, thus preventing any risk of injury from flying debris or contact with the rotating shaft. Lastly, there will be a hazard light on top of the drill near the motor to indicate to bystanders that the drill is in operation.
The most significant change in our electrical system is our custom circuit boards. These circuit boards have been carefully designed by our team with the intent to reduce electrical system complexity and provide a solid foundation for our team in future years. Our custom circuit boards create a generic sensor network which utilizes a versatile communication protocol that allows for easy redundancy and plug-and-play expansion. This is an improvement over our previous system. Instead of having one central location where data is collected and filtered, it is now distributed across many different sensor circuit boards on the drill. This reduces computational load on the processor that will run the automation algorithm, which will increase our algorithm response time. With all these changes, improvement to our downhole sensor have also been made. This sensor will communicate wirelessly to the drill sensor network and will monitor the orientation of the bottom of the drill string and forces applied there. This data is invaluable to our algorithm as it can be used to detect a potential catastrophic failure to the drill string during the deviated drilling process.
Our plan to deviate our wellbore is to use a steel whipstock to force the bit to deviate while the string continues to rotate. First, we will drill a vertical hole 16 inches from the surface. We will trip out, insert the whipstock, and trip back in to kick off at a depth of 4 inches from the surface. This whipstock design will create enough deviation to get us to TD. Our fluid system design is similar to our design from last year. We will use a foam-based drilling mud consisting of surfactant, water, and air. The surfactant water solution will be pumped into the agitator where it will be mixed with compressed air. New additions to our design include a flow sensor to measure and report the flow rate of the fluid. This data will enable the control boards to autonomously vary the pump rate. Our design will be able to provide the transport ratio necessary to remove cuttings of several different rock types.